In this lecture, we're going to be a little bit more precise about what we mean when we say control theory. And I've been throwing around this term controls quite a bit so far, even though we've only seen one lecture. And what I want to do now is make this a little bit more precise so that we get a slightly better understanding of what it is that we're going to be doing in the class. And ultimately, controls, it deals with dynamical systems. These are abstractions that describe something that changes over time. This could be a car that's moving. This could be the price of a particular stock. But ultimately, controls is dealing with how can we best or how can we influence this change of the system. And some examples, and we're going to see all of these examples in the class, of systems that one can control would be robots, epidemics. You could come up with vaccination strategies, stock markets, thermostats for keeping the temperature pleasant indoors, electrical circuits, DC engines, power grids, or autopilots on aircraft. And all of these will show up, and we'll see which of these are easy to control and which of these are actually very hard to control. And we're also going to understand what makes certain systems harder to control than others. I put robots in red, though, because this, at the end of the day, is the main focus of the course from an application point of view. So let's start with trying to build up a control system in terms of the basic needed building blocks. And the first thing you need is some way of describing what the system is doing, or more importantly, where it is. If I want to control a car, let's say I want to build a self-driving car that drives from my home to my office, well, I need to know where the car is. And central to this is the notion of a state. The state represents what the system is currently doing, what state it is in. And we're going to use X to describe what the state of the system is. This could be the position or the velocity of a robot. This could be the percentage of people that are infected by a certain epidemic. This could be a number of different things. But ultimately, the state is the key thing that describes what the system is up to. And what it is actually doing is the dynamics. And the dynamics is the description of the change of the state as a function of time. Now, this is all good, but we want some way of influencing this. So we're going to have a reference signal that is going to, we're going to use it as a way of telling the system what it is that we want it to do. So the reference could be set a cruise controller to 60 miles per hour, or make me a certain amount of money on the stock market, or make the temperature in the room 70 degrees. What do I know? Now, we can do that all we want, but let's say that we want a cruise controller to go at 60 miles per hour. That's not going to work until we can actually measure how fast the system is going. So we also need an output. So we're going to use R for the reference, Y for the output. And the outputs are the things that we're able to get out of the system. This is telling us what the system is doing. So we can't always measure the state. Y is the output. Now, this picture is actually a blatant lie, because if I tell the stock market to go make me a certain amount of money, there's no way it's going to do that. Or if I just yell 65 at my car, it's not going to go 65 miles per hour. So we need some way of mapping reference signals into actual control signals, the inputs. So U is going to be the thing that takes the reference and produces a control signal that then hits the state of the system. Now, this is all fine and good, but this control design is not particularly good because the control signal has nothing to do with the measurements. So we need the final building block, which is the feedback. This is a mapping from outputs to inputs, in the sense that what we're doing is we're taking Y here. We're taking Y here, say Y, and then we're taking the reference, and out here comes the reference minus Y, which is going to be the error in terms of how the system is performing. And this error is translating into some control signal that's then hitting the system. So this feedback mapping is really the key to doing any kind of controls in an effective way. Good. So now that we know a little bit about what are the basic building blocks, I want to talk about the examples just so we can try to understand what these building blocks actually represent. So the state of a robot is typically, if it's a mobile robot on the ground, it's the position, maybe the orientation of the robot, maybe the velocity of the robot. The state is ultimately what we need to describe what it's doing. If it's a manipulated robot, it would be the angles, the joint angles of the various segments of the robot. So that would be the state. The dynamics simply says how the robot is moving. The control signal, or the control input, would be things like velocities or torques or accelerations. So ways of moving the robot around. And the measurements would be things like, where is the robot? What is it seeing in the environment? The epidemics, like I said, a state would be maybe what percentage of the population is infected. The thing we can control, so the input would be vaccination strategies. In this case, the output is tricky. It's very hard to know what percentage of a population is infected, for instance, with an infection. So there, the output would be some kind of measurements at hospitals of how many people show up with this particular disease. Stock market, the state could be, in fact, no one really knows what the state is of the stock market, which is why, in part, it's so hard to make money. The output would be, well, the prices of the stock, and the input is simply buy or sell. Thermostats, temperature, output is temperature. The thing we control is turning things on or off. Circuits, typically the state would be currents, voltages and currents, and the inputs are typically voltages that you're applying, and the outputs are measured currents and voltages in the circuit. Engines, you can apply typically voltages and outcomes, say torque. The power grid, well, the state there somehow is power consumption across the different modules. The things you can control are putting loads and generators onto the grid, maybe. Same thing with autopilots on aircraft. The states would be positions and velocities. The things you can control are accelerations or change the control surfaces of the aircraft, and the measurements are a whole bunch of things. How fast is it going? Where is it going? What's the altitude? What's the wind resistance? And things like that. So what we need to do is come up with a rather general way of describing all of these systems in a way that makes sense, that we can use, and that we, more importantly, can use to control mobile robots.